In digital computers, there are three major ways that we represent signed integers. The first is signed magnitude, then there's one's complement, and then two's complement, which is the most popular. In this video, we are going to investigate signed magnitude representations of signed numbers. And to do that, we want to first understand how we do signed numbers normally as humans. So here is a very human-like number, 137. I say human-like because it's in decimal, not in binary. We'll understand it in decimal first, and that'll make it easier for us to understand the transition to binary. Now we might write 137, but what we technically mean is that this is positive 137, which really just means that it's 137 greater than 0. Now if we wanted to negate a number like this, so let's say we want to negate the number 137, which is really positive 137, then that's going to give us negative 137. Now you see the fantastic mechanics I did here. To negate positive 137, I switch the sign from the positive symbol to the negative symbol, or from the plus character to a minus character. And this is effectively all we do in decimal to represent such a fact. Now, we can expand this and also understand that the negative of negative 137 is actually the same thing as positive 137. And this really is only worth noting so that we can remember that whatever type of number we have, whether it's already positive or it's already negative, we can still negate it. But in doing so, we are just flipping the sign. So if we have a positive number and we want to negate it, we'll go from the plus symbol to the minus symbol. If we have a negative number and we want to negate it, we replace the negative symbol with the positive symbol. Now, this also gives us a little bit of insight into our basic understanding of what signed magnitude representations are, because this in decimal is effectively a signed magnitude representation. So here's a number line that has 0 in the middle, and somewhere over here is positive 137. To the left of this, the same distance away, at least as best as I can draw it, but in the opposite direction from 0, is negative 137. So with a signed magnitude representation here in decimal land, what we're really saying is that a number has two parts. So here's a number like negative 137. Here's a number like positive 45. There are two parts to these numbers. The first is the sign. And here is one of them. It's negative. And over here is another example that's positive. So each number in a signed magnitude representation has a sign, whether we choose to write it on paper or not. It also has a magnitude, and the magnitude effectively just tells us how far away from 0 is this particular value. So this value is 45 from 0. This value is 137 from 0. But when you combine the magnitude with the sign, we determine that this value, negative 137, is 137 away from 0 in the lefterly direction of our number line, or to the negative effect. If it was a positive 45, it would tell us that we need to go to the right on the number line, or in the positive direction above 0, 45 units. And that's the basics of signed magnitude in decimal. Now when we go to a digital computer, the only thing that we really need to add to this conceptually is some limit to the representational size. So let's say we have a 5-bit signed magnitude representation going on. That means we have 5 bits, like this. Whoa, that's almost perfect. And we must have some portion of this represent the sign, and some portion of it represent the magnitude. And the way we've decided to do this is we take the high ordered bit. We call it the high order bit because each bit number is the order of its exponent. So this is the 0th order, 1st, 2nd, 3rd, 4th order in our normal positional mechanisms. But we take this high order bit and we reinterpret it as the sign bit. The remaining bits in the lower order bits are interpreted as the magnitude. Now the magnitude is really easy in a sign magnitude representation. It works exactly like the positional numbering systems we've already seen with unsigned integers. The sign bit, on the other hand, is a little bit tricky because we can't just put a negative symbol in the sign bit, nor can we put a positive symbol in the sign bit, because we only have zeros and ones. So when it comes to the sign bit, the sign bit is going to hold a 0 whenever the value is positive. So it's the replacement for the plus symbol. And when we put a 1 in it, that's going to mean that that particular value is a negative value. Now, it's easy to imagine why we chose to assign positive to 0 and negative to 1 rather than the other way around. And to give you a simple example of this, if I wanted to write the number 5, in binary, I could write 101. And this is 4 plus 1. And so that's 5, at least as an unsigned value. Now I can add a 0 to the front of this, and while still being an unsigned value, just with a weird extra 0 here, it's still the value 5. So the idea being, if we had a 5 originally in just those 3 bits, and we added one more bit with which to provide a sign, by putting a 0 there, then and treating the 0 as positive, the signed value positive 5 would be interpreted the same way if we treated it suddenly as an unsigned value, because in its unsigned interpretation, where there is no sign bit, this is just the number 5 as well. So it makes a lot of sense to use 0 for positive and 1 for negative. So now that we've got this representation figured out, let's look at some possible values and decode their actual meaning. So let's put some 5-bit values down again. We're going to do 5-bit signed magnitude. And I'll give us some bit patterns. Again, recall that we have the sign bit up here. And the rest of this stuff is the magnitude. Okay, so let's get some bit patterns here. How about 10101, 01010, we'll just flip some bits there. 11100, that's a good number. 10111, and 01101. All right, so we got a handful of these numbers, and the thing to remember is that the highest order bit is the sign bit when we're interpreting a bit pattern as if it is in a signed representation. So from this, without doing much else, we can immediately determine the sign of each of these values. So wherever there's a 1, we know that this is a negative, and I'm marking this in red just to match the red of the sign bit. Here's a 1, negative, 1, negative. And everywhere we have a 0, this is going to be a positive number. Positive, positive. Excellent. All right. Then all we have to do is find the magnitude and then add that to the end, and then we've converted these things into our human understanding. So let's see here. 0101. So this is the 4-bit and the 1-bit. So 4 plus 1 is 5. This is the 8 and 2-bit. 8 plus 2 is 10. 8 plus 4 is 12. And 4 plus 2 plus 1 is 7. And 8 plus 4 is 12. Plus 1 is 13. And so we find out that each of these bit patterns are negative 5, positive 10, negative 12, negative 7, and positive 13, respectively. Now, realistically, there's only so many different numbers we're going to be able to represent in sign magnitude or any other representation if we're limiting ourselves to numbers that have 5 bits. So one thing we obviously need to do is figure out what the range of representable values actually are given our 5-bit sign magnitude representation. Hopefully from there we can expand to some arbitrary number of bits, like if we're on an n-bit system. So let's figure that out real quick. Our range is the question. And sign magnitude is such a simple representation where you just say how far away from 0 here, and then whether it's positive or negative here. We can easily come up with the bit patterns for the largest and smallest values we can represent with 5 bits. So the magnitude for each of these values is going to have those lower 4 bits maxed out at all ones. I'm running the lower 4 bits on each side. But on the high end, the positive end, we're going to have a 0 in the sign bit. And on the low end, we're going to have a 1 in the sign bits. So just as a reminder, I'll underline the sign bits here in red. So this is a negative value, and this one is a positive value, and they define the range. So this here is negative, and this is 8 plus 4 plus 2 plus 1 is 15. All the way up to a positive, 8 plus 4 plus 2 plus 1 is 15. So our range with a 5-bit sign magnitude representation goes from negative 15 to positive 15. But if you think about these numbers carefully, it should alert you to an interesting anomaly. That is that we have 5 bits. 5 bits, each of which can take on 2 different values. And so that means we have 2 to the 5th bit patterns that are possible, which is really 32 bit patterns. But if you count the numbers between negative 15 and 15 inclusive, we'll find that we actually have 31 values. And so we appear to be missing one, 31, 32, 31, 32. Where did it go? Well, it didn't really go anywhere. It's just that we have an unusual value in there. And that is negative 0. Because the sign magnitude, we can have any magnitude whatsoever and just put a sign in front of it. So we have a negative 0 in this representation as well as a positive 0. And the way they look is, for negative, we'd have a 1 in the sign bit to indicate negative, and then all zeros for the magnitude. For positive 0, we'd have a positive 0, or a 0 in the sign bit to indicate positive, and then we'd have a magnitude in the remaining bits of 0. So we actually have 2 versions of 0, and mathematically they're equivalent. So negative 0, for example, isn't 1 away from positive 0 or vice versa. They're effectively the same value, and most mathematicians will probably tell you that 0 has no sign. It's neither positive nor negative because it doesn't have any magnitude away from 0. But in computers, when we have a sign representation, there's going to be a 0 or there's going to be a 1 in that sign bit. And so we have to interpret the value as positive or negative. And that means, in this representation at least, that we can actually have a negative 0. And that's where that 32nd bit pattern comes from. So in returning ourselves then to the question of range, we actually see that we basically are going to have the complete range of values, but we're going to have 2 zeros. And in the negative section, we're going to have the numbers from 0 to negative 15 for 5 bits. And that's half of the total representational power of 5 bits. In the positive half, we're going to go from positive 0 to positive 15. Right? Each of those 2 halves being 16 numbers, half of 32. And so we can then expand this understanding into the grander range and say that if we have n bits, then what we're going to end up with is a range that goes from negative 2 to the n minus 1th plus 1, all the way up to 2 to the n minus 1 minus 1. And just to demonstrate these equations in practice with the values that we're using right here, a 5-bit sign magnitude. 5 would be n, so n minus 1 on both sides is 4. And 2 to the 4th power on both sides is 16. So here we have negative 16 plus 1 gets us negative 15. So it shows us our lower end. Here again is 2 to the 4th power, which is 16, minus 1 is 15, positive, because this whole thing is positive. So we go from negative 15 to positive 15. All right, now we've taken some bit patterns in our 5-bit sign magnitude representation and we've interpreted them for their decimal meaning. We've also determined that the range given a 5-bit sign magnitude representation can hold the values between negative 15 and positive 15. So now we're going to do the opposite of what we did here. Instead of starting with the bit patterns, we'll start with some target decimal values and figure out how to convert them into our sign magnitude representation. So let's do this for the numbers 6, negative 11, so really we mean positive 6 here. Negative 11, negative 13 sounds good. 3 and negative 4. So for 6, we see that it's positive, so in the sign bit we're going to put a 0. Let's do that all the way down and do these conversions somewhat mechanically. Here for negative 11, we know that this is going to be a negative, so we're going to put a 1 in the sign bit. We know this is negative, so we'll put a 1. Here's a positive number, so we'll have a 0. And a negative number, so we'll have a 1. Now we need the remaining 4 bits for each of these values to depict the magnitude, or the absolute value of these decimal things on the right. So we need the 4-bit version of 6, and that'll be no 8s, a 4, a 2, and no 1s. So 4 plus 2 is 6. For 11, we're going to need 8 plus 2 is 10, plus 1 is 11. For 13, we'll need 8 plus 4 is 12, and then 1 more than that is 13. For 3, we'll have no 8s, no 4s, and then 2 plus 1 is 3. And for 4, we'll have no 8s, a 4, and no 2s and no 1s. And so we're able to calculate fairly simply what the binary representation of a given sign and decimal value that's within the appropriate range. Well, we can figure out what that would be. All right, now lastly, I want to look a bit at how these numbers, how these bit patterns flow together from bit pattern to bit pattern. So we're going to switch briefly to a 3-bit sign magnitude representation. And I'm going to write out all of the 3-bit patterns there are in order, starting with all zeros. That's 3 zeros. Then we go to the next value in order, which would be 0, 0, 1. And, oops, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. And if we look at each of these, and you're going to see this kind of number table quite often, we can see that these look like binary numbers, and we'll think of them as unsigned binary numbers when we're trying to point out which one it is, because while 3 bits it's easy enough to say, hey, look at the row that has 0, 1, 1. When we get to larger numbers of bits, you know, say 32 bits or even 16 bits or really even 8 bits, it's hard to identify a row by listing its binary pattern. Instead, we deal with these in terms of what we call minterms. And the minterm is just the unsigned equivalent of these values. So this is row 0, 1, 2, 3, 4, 5, 6, and 7. So you'll hear me use this term minterm to refer to a specific thing. So when I say the minterm 5, what I mean is given however many bit representation, how many bits we have in our representation, regardless of whether it's signed, unsigned, sign magnitude, 2's complement, binary coded decimal, whatever it may be, you would just write down that many bits to represent the unsigned value of, say, 5, if I said min term 5. And then we would reinterpret what those bits mean in our actual representation. So if this is the pattern, what do these numbers equal? Well, all of the top half here, these are all positive numbers. Right? So this is a positive, a positive, a positive, and a positive. We can tell that because the sign bits have 0. Over here in the bottom half, these are all negative numbers, and we can tell that because the sign bit has a 1 in each of the rows. From this, then, we can just look at the bit patterns remaining in the bottom 2 bits, the low order 2 bits, to come up with the magnitude. So this is really a magnitude of 0. This is a magnitude of 1. This is a magnitude of 2 and a magnitude of 3. And then those same bit patterns repeat, 0, 0, 0, 1, 1, 0, and 1, 1. So we're going to see negative 0, negative 1, negative 2, and negative 3 here. Now the reason that this is interesting is because this table is in the natural representation of these numbers as we move. As we start here and we add 1 to the value, we go down here to this next one. And that's reasonable. 0 plus 1 is positive 1. If we add 1 again, we'll continue to go down, and then we can continue to go down. But there's still half of the bit patterns left, and if we were to add 1 to a positive 3, since we don't have positive 4 anywhere else, we would have to wrap around, kind of like an odometer going from all 9s to all 0s, to whatever the lowest number is in our representation. We overflow the capability of our representation. And so we would have to suddenly go from positive 3 all the way down to negative 3. So we take a weird jump from the middle to one end. Now, if we continued to add 1, unlike up here where we moved down the list, we couldn't move down the list here because if we did, we would wrap back around up to here to a positive 0. And negative 3 plus 1 is not positive 0. Negative 3 plus 1 is negative 2. So you see, as we add 1 in this half, we tend to go down. When we add 1 from this half, we tend to go up. And then still there is the other anomaly of the fact that we have some circumstance where we might have a negative 1, and then we add 1 to it. Will the result be negative 0 or positive 0? Well, we're not going to concern ourselves with that very much because our interest here is really in seeing that the representation of using one bit for sign and the rest of the bits for magnitude is a natural extension of what we do in the human world with decimal values written on paper. But it's not necessarily all straightforward from there, right? The flow that moves around through the numbers, adding 1 going down the list or going up the list, depending on what number you're adding from, that's unusual. We have some number of bit patterns that are unique, and yet one of them gets taken from us because it represents effectively the same value, negative 0 and positive 0. And so we want to deal with these problems and make it all a little bit simpler so that we can make the mechanics of our computer systems a little easier to manage. Because developing the circuit, say, for the sign magnitude addition is going to have to take into account the sign magnitude caveats. Right? So we need to look at other possibilities. And the two other ones that we consider are 1's complement representations and 2's complement representations.